Good morning, everyone. Welcome to the Toronto Geometry Colloquium.
This is a weekly web series all about geometry processing, which aims at promoting young researchers and researchers from traditionally underrepresented communities.
Every week, we will have an opener talking about their cutting-edge research for 10 minutes, followed by a headliner giving us a keynote presentation.
Today, we are thrilled to have Astrid Bunge as our opener to talk about the polygonal Laplacian, and Oded Stein to discuss his research on the Bilaplacian operator. You're encouraged to leave all your questions in the YouTube chat. You're even more encouraged to leave them as you come up with them, not at the end of the talk, so that helps us curate a better Q&A session at the end. So let's begin with Astrid Bunge, who is a PhD student at the University of Dortmund, supervised by Mario Bosch. She has a bachelor's degree in mathematics, a master's in intelligent systems from Bielefeld University, and her current research focuses on the more mathematical side of geometry processing. Her latest paper, which she will present today, introduces a smart and deceptively simple way of generalizing the traditional cotangent Laplacian to general polygonal meshes. She is also our first speaker based in the European Union, and the first of our speakers to have on her website a full 3D scan of her head. You can Google that. Please join me in welcoming Astrid Bunge to our colloquium. You can take it away now.
Thank you very much. Let me just share my screen. Okay. Well, thank you for having me and for the nice introduction. And yeah, as already mentioned, I will tell you something about our recent paper, Polygon Laplacian Made Simple, which we presented on the Eurographic this year. So you all probably know about the Laplacian operator. It's a ubiquitous tool in geometry processing because it's involved in solving many PDEs. It's closely related to curvature and signal processing. So we all probably faced an application where we had to use it. And the idea was, and basically triangle meshes are the more or less standard surface representation in our field. So the discrete Laplacian or Laplace-Beltrami operator has been well investigated for this shape, with the cotangent Laplacian being the more or less standard everybody's using. But polygons, although they fulfill very nice features and are very present in our field, receive far less attention, which is very unfortunate since they are very awesome. And having an operator that works on any kind of mesh and not only triangles seems actually very desirable. Of course, the question arises, if we are so well versed in dealing with triangles and are faced with a polygon, why not simply triangulate it? Well, for example, with the quad mesh, the edges often align with the principal curvature directions. So simply triangulating it would break the symmetry of the shape and would lead to noticeable artifacts, which is not desirable. They had a purpose. One could argue that inserting a new vertex inside of each polygon would not break this property and keep the symmetry, but then of course we would get additional degrees of freedom, increase the whole system's dimension, and that's of course not desirable. So not altering a mesh and being able to apply a polygon Laplacian is a nice feature and a good way to go. And actually this field has received some attention over the years, even with the current SIGGRAPH, which even a publication on the last SIGGRAPH conference. And we wanted to be part of the team because our idea was, if we are faced with a polygon, why not make use of the triangle operators? And by inserting a virtual vertex inside of each polygon, just span an implicit triangle fan in the polygon, compute, for example, in our case, the cotangent Laplacian, and distribute the values back to the original polygon, hiding all the stuff we have done before. And to achieve this, okay, basically what we are doing is we interpolate basis function on the head of the head basis functions of the triangles to new basis functions on the polygon, being able to interpolate functions on the original mesh. Okay, as a short reminder, what do we need? For the cotangent Laplacian, it's divided into a stiffness matrix S, which is more or less its name giver since it contains different cotangent weights, and in the inverse of a mesh matrix. In our case, it roughly assigns each vertex a third of the surrounding triangle areas. So to achieve a polygon Laplacian, we also have to find a stiffness and a mesh matrix. To do this, we make use of the multigrid method. It basically says that if we are given different resolutions of a grid, we can transfer informations from the fine version to the coarse grid via a restriction operator, and going from the coarse to the fine one with the help of a prolongation. And that's basically what we are doing, because we go from a polygon to a finer triangle mesh with the help of a prolongation and transfer the information back with restriction matrix. So right now we have to find these two operators. And the prolongation for it is not that difficult, because we want to retain the initial polygon vertices. So we start with a diagonal identity matrix to retain those. And the virtual vertices are just affine combinations of the polygon's vertices. So by appending additional rows for each polygon with the weights inside, we are already done and obtain the virtual vertices, retain the previous ones, and have our prolongation. On this mesh, we can then compute the cotangent Laplacian, which everybody of us has probably done in our lives so far, and have to focus on the restriction. Well, on this, here, math is our friend, because by definition, the restriction operator is the dual of the prolongation. And since we only have to face real valued matrices, we are more or less already done, because for real valued matrices, the dual is simply its transpose. So we already have the prolongation, we take its transpose, and then we have the restriction that gives us the information back to distributes the information back to the original vertices. So how do we combine all this information? Okay, so we compute the triangle cotangent Laplacian on the implicit mesh, and then sandwich it with the prolongation and restriction operator, giving us a new stiffness matrix with the same dimension as polygon vertices. The same can be done for the mesh matrix. Compute the mesh matrix on the triangle mesh, sandwich it together with prolongation and restriction, and in our case, we choose to lump it to a diagonal matrix. This is not necessary, but makes inversion of the mesh matrix easier, but you can just choose the way you want to take your mesh matrix. Of course, the one question remaining is, what virtual vertex do we want to choose? It should be unique and easy to compute, because we have to do it per phase. And the first idea we had was to simply use the centroid. We have uniform weights for each vertex, and it's just very easy. Unfortunately, for non-convex shapes, this virtual vertex can lay outside of the polygon. Outside, of course, only being defined for planar polygons, but even then, we get undesirable triangle flips leading to bad cotangent weights, and which our operation cannot recover. So we had the idea to penalize big surface areas and push the vertex back inside of the polygon by finding the minimizer of the sum of the squared triangle areas. And with this, we obtain nice triangles and are able to compute a good cotangent Laplacian. And finding this minimizer with respect to the weight is actually also not that difficult. We can define this energy we have to minimize with, of course, once again, we need those affine weights. So we have this condition. Affine weights is necessary to fulfill all the properties or retain all the properties of the cotangent Laplacian. But even then, differentiating this energy with respect to the weights is solvable through a linear system, which is easy enough to do, and gives us a unique point per polygon to span the implicit triangle fan. And of course, then we have again the weights for the prolongation operator. So how does our operator perform? As a nice qualitative application, for example, we implemented the conformalized mean curvature flow, which lets a shape converge to a more and more spherical shape after some time steps, which is so more clearly working, as you can see. For a quantitative measure, we compared the mean curvature of different tessellated meshes on a unit sphere, which should be 1, to test the accuracy of our operator. And as you can see here, with the normalized error, our operator performed quite well compared to the back then state-of-the-art Polygon Laplacian by Alexa and Badetsky with different hyperparameters, and simply triangulating the mesh and computing the cotangent Laplacian. Another nice feature of our Laplacian is, since the Laplacian is defined as the divergence of the gradient, we are able to decompose our stiffness matrix into a divergence and gradient operator, which is, for example, needed for the heat flow by Keenan-Crane et al., which computes the geodesic distances. And if I do this, you can see we obtain very nice results. But if I have to do it for the Alexa and Badetsky Laplacian, the result is clearly distorted. And I have to adjust the hyperparameter, which they introduced in the paper, to get better results. And this hyperparameter does not have an obvious interpretation. So I have to find a suiting one, but I cannot say, okay, for this application, I would need 0.3 or whatever hyperparameter to be able to do that. So we are way simpler to apply. And once again, to emphasize, our method is not equivalent with simply inserting a vertex. For example, once again, you can see the results of the geodesic distances with our operator. But if I now insert the virtual vertex explicitly into the mesh and triangulating it with it, the results are once again a little bit distorted by simply computing the cotangent Laplacian. So using the restriction operator on our stiffness matrix does give us a different results. And to summarize, we were able to find a discrete Laplacian operator for polygon meshes by inserting a virtual vertex per polygon. And we hid all the construction behind two matrices to obtain a stiffness and mass matrix, which we can apply to all applications and just use. We inherit all the desirable properties of the cotangent Laplacian, and we are even on par with current state-of-the-art polygon operators, while being way simpler to use because we do not have any hyperparameters to tweak. And if you're interested, there are more details in the paper. For example, we are consistent with finite elements exterior calculus, and we are also slightly faster than the Laplacian presented by Alexa and Badetsky. And yeah, if you want to check our source code out, you can find it under the following link. And with that, thank you for your attention.
Thank you very much, Astrid. That was an amazing presentation. I think we all thoroughly enjoyed it. As we mentioned before, we won't have a Q&A now. We will have a combined Q&A at the end. So you can ask your questions to Astrid on the live chat now, and we'll ask her after Oded's presentation. So let's move on to our headliner today, who is Oded Stein. He's a postdoctoral fellow at a small, humble American university called the Massachusetts Institute of Technology. He just got his PhD in mathematics at Columbia University under the supervision of Professor Eitan Griswold. He's one of these people whose publication history is very well tied together to a common topic, and with whom you get the feeling that there's like a higher narrative to every project that he works on, which I would summarize as just take some graphics application, and if you see a Laplacian there, change it to a Bilaplacian and see what happens. During his PhD, he spent a lot of time in our Toronto lab, and I can personally vouch for the fact that he's a very selfless, helpful colleague to have and to work with. And also a great friend to have conversations with about basically anything. Just don't tell him that you think that Swiss cheese always has holes in it. Please join me in welcoming Oded Stein. You can go ahead now.
Thank you very much. Let me share my screen. Perfect. Is my presentation visible? Thank you. Yep. Well, thank you very much. And thank you to Sylvia, Derek, and Sangbei for inviting me. And I'm honored to have been preceded by Astrid, whose interesting research neatly leads into what I'm going to talk about now. For the next 40 minutes, we will talk about the Bilaplacian and its associated partial differential equation, the biharmonic equation. I'll talk a bit about its history, about where we can find the biharmonic equation in science, how it's applied to geometry processing, and then also a little bit about my own work on the biharmonic equation. Here's a small outline of what we will do. First, I will introduce the Bilaplacian and tell you how it differs from the Laplacian. Then we will look at what we can do with the Bilaplacian. What are its applications? Then we will look at a discretization of the Bilaplacian for triangle meshes and ask ourselves whether this is a good or a bad discretization. And at last, we will look at different boundary conditions that we can apply to the Bilaplacian and how these boundary conditions influence our results, with a focus on how we can get results to be as independent of the boundary shape as possible. Let's first talk about the Laplacian. You might remember the following definition of the Laplacian for flat surfaces in R2. The Laplacian of u is minus its second derivative in x minus its second derivative in y. The Laplacian for flat surfaces appears, for example, in the equation for the electric potential. The Laplacian of the potential is equal to the sum of all charges. On the right, you can see an example of an electric potential where the potential is arbitrarily fixed to be 1 and -1 at 2 points, and its Laplacian is 0 elsewhere. You might also be familiar with this definition of the Laplacian, which is the definition that is also valid for curved surfaces in R3. The Laplacian of u is minus the divergence of the gradient of u. This Laplacian, which coincides with the above definition for flat surfaces, appears, for example, in the heat equation. On a heat-conducting material, the Laplacian of temperature will always be 0 in the long run, i.e. in the stable limit of infinite time. Here on the right, you can see a tube whose temperature has been fixed to -1 on one end and 1 on the other, and the resulting temperature distribution obeys this Laplace equation on the curved surface. The Laplacian is extremely useful for so many things in geometry processing. It's one of its most fundamental tools, and we've just seen a few examples of it in Astrid's talk earlier. In fact, it has been called the Swiss Army knife of geometry processing. You can use it for a large variety of things, and I can't do justice here to the large variety of applications, so I suggest you go and watch the course that I'm citing here for a great introduction to the Laplacian. One of the properties that makes the Laplacian so great is the fact that it smooths out everything. Here is some function, and I did a smoothing operation using the Laplacian. It's much smoother and less noisy now. So the Laplacian can smooth things, and since it's a partial differential equation, we also specify a boundary condition for the smoothing operation, either a value of the function at the boundary or its normal derivatives. So those are the two properties of the Laplacian we like. It smooths everything, and we can pick either values or derivatives at the boundary. We can use this smoothness property to interpolate with the Laplacian as well. Consider the following simple interpolation problem. We have this bar-like domain, and then we solve the following interpolation problem. U at the left end is 1, U at the right end is -1, and the Laplacian of U is 0 everywhere. Well, what we actually mean when we say the Laplacian should be 0 everywhere, what we want as a result of an interpolation is that the resulting function is smooth everywhere. So give us a very smooth function that fulfills these conditions here that we care about. So this looks nice. We have a really smooth ramp from right to left. It fulfills the conditions that we wanted, and it is very smooth. But what do we do if we want a little bit more control over our function? What if we also want to be able to prescribe the normal derivative on the left and on the right, but still have a very smooth function u? Well, we cannot do this with just the Laplacian. We can only pick one boundary condition if we want to solve the Laplace equation, either values or normal derivatives. There is a way to get a very smooth function where we prescribe both values and boundary conditions, and we will be able to do it with the Bilaplacian. Here is a slightly more complicated example of when we want more control over what happens to our interpolation. Consider this image, which we want to animate by moving around handles which are placed at the eyes of the person in the image. The details of this are not very important. You just need to know that we can compute a deformation that is very smooth using the Laplacian as a starting point. However, if we do that, we find that the Laplacian result is not that smooth around the handles on the eyes themselves. You can see this sort of spike-like deformation behavior, while outside of the handles, the deformation is smooth. And there is a way to get deformations that are smooth around the handles as well, and we can get it by using the Bilaplacian. Here is another example of where spikes can appear when using Laplacian-derived methods. We have this bunny, and we are employing a surface flow to smoothly deform it to a sphere. Now, this flow is actually a lot more complicated in practice than I'm making it sound right now. But what you need to know for the purposes of this example, that this is a flow using the Laplacian. Using a Laplacian-like surface flow flows the bunny into the sphere, but the intermediate stages show this spiky, non-smooth behavior. And a Bilaplacian version of this flow will give us non-spiky, nice, smooth intermediate results. And if I'm not mistaken, this is the exact same paper for which we have seen an application of Astrid's Polygon Laplacian earlier, the robust fairing via conformal curvature flow. So even though the Laplacian is immensely useful, there are scenarios in which the Laplacian alone does not give us enough control, or where the Laplacian results in potentially undesirable spiky behavior. This is the basic Poisson equation, one of the Laplacian's basic partial differential equations. And this Poisson equation allows us to specify either values or normal derivatives at the boundary. How can we increase the amount of control we have at the boundary? Well, instead of looking at the Laplacian, we look at the Bilaplacian, the Laplacian applied twice. The Bilaplacian's corresponding partial differential equation is the biharmonic equation. With the biharmonic equation, at the boundary, we can specify the value as well as the normal derivative at the same time. Remember, the Poisson equation models a variety of physical systems, for example, the potential of an electric field or the steady state of heat. What does the biharmonic equation model? Well, the biharmonic equation models the displacement of a thin, bending-only flat plate. This is also a very smooth operation, so the biharmonic equation is also a great candidate for getting smooth solutions to things. And fixing the boundary values as well as the normal derivatives at the boundary corresponds to physically fixing the plate as well as clamping it at the boundary. Here is a flat plate, and here's that same plate bent, but while being fixed and clamped at the boundary. The result is a very smooth function, but we can now control both values and derivatives at the boundary. Okay, so the Bilaplacian can give us more control at the boundary than just the Laplacian, but it can do more. It can also help us to avoid these pesky spikes we saw in earlier examples. Consider these two disks. The left one behaves like a thin rubber sheet, a physical system modeled by the Laplacian. The right one behaves like a thin metal plate, a physical system modeled by the Bilaplacian. A finger will now poke the middle of these plates while keeping the boundary fixed. This is what happens with the Laplacian on the left. We get a spike where the finger poked, or to be more mathematical, where we put an isolated point constraint. This makes sense intuitively when you think about how a sheet of rubber behaves. If you have a sheet of rubber at home, go try it out, fix the boundary, and pull up the middle. This does not happen with the Bilaplacian. We get a nice dome-like shape where the finger poked, because that is how bending thin plates works. Now, remember the two examples I showed you earlier where we saw spiky behavior with the Laplacian, but smoother behavior with the Bilaplacian? And this kind of argument, in more complicated version, helps explain what we see there. So because of its mathematical properties and the physical systems it corresponds to, the Bilaplacian can give us more control over the boundary than the Laplacian, and it can also give us less spiky results, which is often desirable. There are many applications of the Bilaplacian. In this and the next slide, I will show you some of them. Using the Bilaplacian, one can compute a distance function for surfaces that is very smooth. This is in contrast to, for example, the geodesic distance function, which measures the length of the shortest curve between 2 points. As you can see on the right leg of this person here, the geodesic distance has non-smooth kinks, while the biharmonic distance is smooth. This new smooth distance function is still a mathematical distance function. It is cheap to compute, and it has certain characteristics of the geodesic distance. For example, it looks a bit like a geodesic distance locally. We can also use the Bilaplacian to deform and animate characters. Using a technique called linear blend skinning, we can pre-compute smooth deformations that are then used to very smoothly deform characters in real time by manipulating a set of predefined handles on the character. This is the technique used to animate the baby images you saw earlier. And using the Laplacian, it is possible to achieve natural deformation behavior without any spikes at the handles. Beyond these applications, there are more where a Bilaplacian is an important part of the method. They include, for example, the efficient simulation of bending surfaces, adding global illumination effects to hand-drawn meshes, make computations on detailed surfaces more efficient by upsampling computations on coarse surfaces, modeling shapes from curves, and many more. Okay, I hope by now at this point, you are all convinced of the utility of the Bilaplacian. But if we ever want to actually use the Bilaplacian for an application, we need to discretize it. Make a version of the Bilaplacian that works with discrete functions on discrete surfaces. The functions and surfaces we can actually work with on a computer. So we need to do two things. We have a surface that we need to turn into some discrete representation, and we need to represent functions on that discrete surface. For the one discretization which we will consider in this talk, the surface is discretized using a triangle mesh. This is very common in computer graphics. Our discrete surface is piecewise flat triangles, which are described by the positions on their corners called the vertices. The function u on the discrete surface omega we will discretize using hat functions. A hat function is 1 on a specific vertex, 0 on all other vertices, and linear in between. So they end up looking like little hats above specific vertices. And a function discretized with these hat functions, phi j, is written as a sum of the uj phi j. We have now discretized the function u since it's completely determined by the scalar coefficients uj. This method of discretizing functions is called the finite element method, and you can read about it, for example, in this book by Bress. Okay, how do we discretize the Laplacian and Bilaplacian triangle meshes with hat functions? Let's start with just the Laplacian. Remember, the Laplacian of u is the divergence of the gradient of u. That's 2 derivatives in u. On the other hand, hat functions are continuous and piecewise linear, so we can only take 1 derivative. How can we use them to discretize? Well, we can rewrite the Poisson equation, Laplace u equals f, into a form that can be written with only one derivative like this. We start by, instead of writing the equation with respect to each point x, we multiply an arbitrary function v and integrate over the entire surface. This is equivalent to the statement on the left, but now instead of a statement for all points x, we have one for all functions v. A mathematical technique called integration by parts tells us that we can put the divergence of a function when integrated onto the gradient of another function, plus some boundary terms, which we'll forget for now. Thus, using integration by parts, we can write the Poisson equation as the following equation for all functions. The integral of grad u times grad v is equal to the integral of v times f for all v. The boundary term from the integration by parts disappears once we apply one of our specific boundary conditions. The important thing here is that this expression now only has one derivative on u and one derivative on v, and is thus ready to apply our hat functions to. Now we need to solve this equation for all v. But this is easy. We have discretized all functions, so it's really easy to check all of them. We just need to check this for all phi j. U is discrete too, so if we write u as a sum of our hat functions, we can write above equation simply as a matrix vector equation, and solving the discrete Poisson equation is the same thing as solving this linear matrix equation. This matrix L is the discrete Laplacian, and the entry corresponding to two vertices I and j with an edge between them is cotan alpha ij plus cotan beta ij, where alpha ij and beta ij are the angles opposite the edge ij, and the diagonal terms Lii are such that each row of the matrix sums to 0. It's usually called the cotan Laplacian because of how its definition involves cotangents. So we had a smooth problem, Laplace u equals f, and we discretized it, so now that we have Lu equals f. However, did we do a good job discretizing the equation? How would we even decide this? Well, we ask ourselves, does our discrete solution converge to the smooth solution? Convergence means basically that the more detail we add to our mesh by adding more vertices and having smaller triangles that better approximate the surface, the smaller the error between the exact solution and our discrete solution gets. Here is such a refinement sequence where we successively add detail to the mesh until we arrive at something that is in the limit the original surface. As we do this, the error between discrete and exact solutions should decrease to 0, and if it does, we say that our method converges and we are satisfied. So here's the important question. Does the solution of the discrete problem with the cotan Laplacian converge to the solution with the exact Laplacian? If this were one of these interactive talks, I would now wait for an answer from you before telling you that, it was a trick question. The answer is, it depends. What does it depend on? Well, we have guaranteed convergence if the following conditions are fulfilled. For each triangle in the mesh, the ratio between circumcircle and incircle has to remain constant and is not allowed to increase under refinement. So this kind of refinement is OK, but this kind of refinement where the triangles stretch is not. The pointwise error between mesh and surface, i.e. the distance between each point on the mesh and the closest point on the surface, can be at most ch, some arbitrary constant times h, the edge length of a triangle in the mesh. Yes, the edge lengths are not all the same, but this is a simplification of the actual condition. And the error between the normals of the discrete mesh and the normal of the smooth surface has to be bounded by a constant times h as well. So if all of these conditions are fulfilled, then we know that the so-called L2 error, the integrated difference between the exact solution or discrete solution, decreases by the order of h squared, where h is the edge length of the mesh. And here I've added a small subscript h to the discrete solution u, because really the discrete solution depends on the mesh, so it also depends on the edge length. How do we know that this is true? Well, this is a famous reference, and the actual result in a less general form goes back to a result from the 80s. And this has been well known for the cotan Laplacian for quite a while. If we fulfill all of these conditions, then we can sleep in peace. We know that our discretization converges. OK, so now we know how to safely discretize the Laplacian in a convergent way. But what about the Bilaplacian? In the same way as we had a weak formulation for the Laplacian, we also have a weak formulation for the Bilaplacian. The Bilaplacian of u is equal to f with 0 function and 0 normal gradient at the boundary, if and only if the integral of Laplace u times Laplace v is equal to the integral of v f for all v. However, this is still two derivatives on u and v here. So just by going to this weak formulation, we are not done yet for the Bilaplacian. It's not good enough to use our hat functions from earlier. Our hat functions are only continuous and piecewise linear, so we can only take one derivative, and Laplace U has two derivatives. So we need to go deeper. Let's introduce a new function w, so that the weak Laplacian of u is w, i.e. for all functions z, nabla u dot nabla z integrated is equal to z times w integrated. Then plugging this into above equation and doing the same integration by parts we did back with the Laplacian, we get the following equation. The integral of f times v is equal to the integral of nabla w times nabla v. Now we only have one derivative everywhere. And that's more, well, like what we want. Now we can use our hat functions. Isn't this great? We took the original biharmonic equation, which had four derivatives, Laplace of u equals f, and we now have the following system of equations. Find the two functions u, w, such that these two equations hold for all z and v we might test them with. All of these only have one derivative, and we can directly write them as matrix equations, like we did before. The first equation becomes Lu equals mw, where L is the discrete weak Laplacian as before, the cotangent Laplacian, and m, also called the mass matrix, discretizes the second integral here. The second equation becomes Lw equals f, where L is again the cotangent Laplacian. With some hand waving, we can discretize the biharmonic equation with the following discrete equation, L m inverse Lu equals f. This is called the mixed discretization of the Laplacian. And as you can see, one of its great advantages is that it's almost as simple to implement as just the Laplacian itself. We're using the same discrete matrix L as before, the COTAN Laplacian. But feel free to, in this exact same discretization, plug in Astrid's Laplacian from earlier. This works for any discretization of the Laplacian. If you want to read more about this mixed method, I recommend the following reference. It gives a great introduction to the mixed method from a computer graphics perspective. So here's the important question, as before with the Laplacian. Does our solution for the mixed discrete bilaplacian converge to the exact solution? Again, it depends. The answer is yes, if, as before, we have that for each triangle, the ratio between circumcircle and incircle does not increase, and if the surface is flat. Well, that's kind of sad. As we saw earlier, we want to use the bilaplacian in many scenarios on curved surfaces, so this result is not really flexible enough. This is a result by Schultz from 1978, so it is really old. What can we say about curved surfaces? What has happened in the meantime? Let's find out. We will follow the method in the following paper to try and prove the convergence of the mixed discretization for the bilaplacian. And here's a small disclaimer for the proof that's about to follow. The proof sketch I'm about to show you is only available as a preprint so far. It has not been peer-reviewed yet. Having said that, let's jump into it. Now, I will only be able to give you a very simplified version of the argument that leaves out some details and hand waves a lot. However, I hope that I can get the main idea of the proof across. In order to do that, we will first get a bit more exact with our language. Until now, we have just talked about a problem for the exact solution and then our discretization of it. That's not really actually all the problems there are, though. So let's be a little bit more precise. This is the exact problem whose solution we want to approximate with our discrete method. The solutions are u and w, and the integrals and the gradients we care about are integrals and gradients on the smooth solution surface omega. This is the exact problem. Here is our second problem. We are still on the surface omega, but now our functions are all hat functions. The solutions tilde UH and tilde WH are hat functions, but they live on the surface omega. So we have discretized the functions here, but not the surface omega yet. And the solutions UH, and here's the third problem. We are now on the mesh, here called omega H, and our functions are discrete hat functions. UH and WH are hat functions which live on the mesh, and here we have discretized the functions as well as the geometry. Only this last problem is the actual discrete problem involving cotangent and mass matrices that we have derived on the last few slides. We only ever compute this last problem in practice. The above problems are just here to help us with our proof. Sorry, my keynote crashes from time to time. Here's the same thing again, a bit simplified. U and W solve the exact mixed bilaplacian on the surface. This means both functions have arbitrarily fine resolution, as well as the surface itself has an arbitrarily fine resolution. Tilde UH and tilde WH solve the discrete mixed bilaplacian on the surface. This means that the functions tilde UH and tilde WH are discrete, but the surface itself still has unlimited fine resolution. UH and WH solve the discrete mixed bilaplacian problem on the mesh. Both UH and WH are discrete, and they are formulated on a discrete surface, our mesh. As a result, you can see the triangles here are shaded flat now. Now, the way we will prove convergence of UH to U is we bound the error between the discrete solutions on the surface and the exact solutions on the surface. The discrete solution on the surface and the discrete solutions on the mesh. And then later on, we bound the error between the discrete solution on the surface and the exact solution on the surface in 2 separate steps. Let's look at the first one of these problems. How do we bound the error between the discrete solution on the mesh and the discrete solution on the surface? I will give you the main idea here again, since I don't have time to present you the actual full proof. It relies on the following observation. For arbitrary smooth functions, in general, there is no way to bound the gradient of a function v by the value of the function itself. Imagine the function drawn here on the right. It can be arbitrarily jumpy, which means the derivative can get very large if you add many more high-frequency jumps without actually increasing the maximum value of the function. So the derivative of this function can explode while the function value stays bounded. By contrast, for hat functions, we can estimate the gradient of the function using the function value itself. The gradient of the hat function is always bounded by a constant times the inverse of the triangle edge length. Hat functions can never have a larger gradient than 1 divided by the edge length, since hat functions are 1 at a vertex and 0 at all other vertices. The line cannot fluctuate arbitrarily like it can with smooth functions above. Thus, the gradient of hat functions can be bounded by a constant times 1 divided by the edge length. We can use this property to compute a bound between the discrete solution on the mesh, WH, and the discrete solution on the surface, tilde WH. The error is bounded by a constant times h to the power of sigma minus 1. What is sigma? Sigma is the order of pointwise approximation of the mesh to the surface. So depending on how well our mesh approximates the surface, we might have an error bound for tilde WH minus WH that goes to 0 as h decreases, which is great because that means convergence. Indeed, for the purposes of this proof, we demand of our mesh that sigma is larger than 3 divided by 2. This is larger than the rate demanded for the convergence proof of the COTAN Laplacian, where we only needed sigma to be larger or equal to 1. But this is OK, since many surfaces that we have in real life actually fulfill sigma equals 2. So we still have a little bit of room there. Now we also need to bound the error between the discrete solution on the surface and the exact solution on the surface. Bounding the error between tilde WH and W is still a bit difficult. So we introduce a second intermediate, tilde RH. It's named like that because this technique is a well-known technique that's called Ritz interpolation. Tilde RH is basically a discrete solution to the same Laplace equation that W is also a solution of, the exact W. Bounding the error between tilde RH and W is almost like solving a normal Laplace problem. So we know that the error here is bounded from previous work. We can now show that the error between tilde WH and tilde RH is bounded by a constant times the square root of h. And we do this with a complicated variety of neat calculus manipulations involving the Laplacian and gradients. Now, using the error bound for the discrete functions from last slide, we can show that the error between W and WH is bounded by a constant times the square root of h. Now, we're almost here. With a little bit more calculus, we can leverage this square root of h bound to actually get an h bound on the solution U. The error between U and UH is bounded by a constant times h. So in the end, we have derived an error bound for the solution of order h. This is worse than the h squared error for the discretization of just the Laplacian. But hey, it's a more complicated equation, and we are discretizing it with elements that are just as simple as we used for the Laplacian earlier. So to summarize, does the solution for Lm inverse Lu equals f converge to the exact solution of Bilaplacian of u equals f? Yes, it converges if, for each triangle, the ratio between circumcircle and incircle does not increase during refinement. So as before, this refinement sequence is OK, as all triangle shapes remain similar. But this refinement sequence is not OK, because the triangles are stretching. We need the pointwise error between mesh and surface to be bounded by a constant times the edge length to the power of 3 divided by 2. Also, as before, we need the error between the normal vectors of the mesh and the normal vectors of the surface to be bounded by a constant times h. This is still a slightly simplified version of the actual conditions, but it captures the gist of it. So if all these conditions are fulfilled, we get an error bound on the solution of a constant times h. Let's put this to test in a convergence experiment. In this specific experiment, I will show you what happens if the triangle regularity, that is the ratio between circumcircle and incircle of the triangles, is not maintained during refinement. Here is a cylinder discretized with the mesh pattern you see below. If we have a regular refinement, then the quantity triangle regularity, which is this ratio between circumcircle and incircle, remains constant. So as the pointwise error of the surface decreases, so does the error in the discretization. By contrast, here we refine the triangles along the vertical axis of the cylinder much quicker than along the equatorial axis, resulting in these elongated triangles. And it gets worse the higher the resolution of the mesh is. Thus, even as the pointwise error of the discrete surface decreases, the error of our discrete solution does not decrease, and the solution does not converge. So these conditions are really important. This particular refinement pattern of a cylinder is known as the Schwarz lantern and is a great example for a variety of degeneracies that occur with the discretization of geometry. Okay, that was quite a bit. We have proved that under certain conditions, the cotangent discretization of the biharmonic equation converges. Well, until now, our Bilaplacian always came with zero Neumann boundary conditions. This means that at the boundary, the normal derivatives of solutions are zero, or they approach zero in some limit. For the bending thin plate, whose displacement is modeled by solutions of the biharmonic equation, this means that the plate is clamped at the boundary. And those gray things are supposed to be clamps. If you look at the isolines of a function, lines along which a function is constant, zero Neumann means that the isolines are perpendicular to the boundary. Here's a little thing to think about, though. The zero Neumann conditions aren't the only possible choice of boundary condition. Let's investigate the exact effects of the zero Neumann boundary conditions, and let's see if there are things for which we might want to use a different boundary condition. In order to do that, we will not solve the biharmonic equation directly. Instead, we will use something called the principle of variation to turn the solution of a partial differential equation into an energy minimization. The principle of variation states that if a function's Bilaplacian is zero and it fulfills the zero Neumann boundary condition, then it must also minimize a certain energy. This energy is the so-called Laplacian energy, the Laplacian of u squared integrated over the surface omega. Now, instead of solving the equation directly, we can minimize this energy with the correct boundary conditions and thus obtain smooth solutions while also obeying additional user-defined constraints on top of just the Bilaplacian, something which is hard to do with the PDE formulation. Let's look at a simple example of trying to use this Laplacian energy with zero Neumann boundary conditions for smoothing. We minimize the following energy to denoise data by smoothing. This energy has a smoothing term, which is the Laplacian energy with zero Neumann boundary conditions, and this energy has a fitting term that relates non-smooth input u0 to the output u, and it has a parameter alpha that varies between fit and smoothness. Here is a reference function plotted as a height field, and here is the same reference function with noise added. We will now vary alpha in order to smooth this and denoise it. We can see that by smoothing it, we have heavily distorted the isolines on this omega shape. The reason for this are the zero Neumann boundary conditions. Zero Neumann means that the isolines of our function have to be perpendicular to the boundary, which leads to bias. Our smooth function does not look like the reference function at all. Now, this does not mean that the zero Neumann boundary conditions are bad. They are not, and many other applications that I've mentioned in this talk use them successfully for their application. However, for this sort of smoothing that should be independent of boundary influence, they are not the best choice. So since the zero Neumann boundary conditions give us boundary bias, let's look for alternate boundary conditions. Let's introduce the concept of natural boundary conditions. Natural boundary conditions are the boundary conditions that emerge when an energy is minimized over all functions without explicitly prescribing boundary conditions, like we just did. So even without any explicit boundary conditions, just from the minimization, some boundary conditions still hold, and these are the natural boundary conditions. Let's try this for our Laplacian energy. We get rid of the zero Neumann boundary conditions, and we see that the natural boundary conditions of the Laplacian energy emerge. Laplace of u is zero at the boundary. So let's try to apply the Laplacian energy with zero Neumann boundary condition, Laplacian energy without zero Neumann boundary conditions to the same smoothing problem as before. We have the same omega-shaped domain with the same height field we want to smooth, and we start with the same noisy initial function, and we vary the parameter alpha to smooth it. Now, this is also not what we wanted. We find that our function was smooth only on the interior, but all the noise on the boundary is still left. compared a smooth result with the reference solution. The problem now is that the space of minimizers is too large. All functions that have 0 Laplacian at the boundary are OK as far as this boundary condition is concerned. And the function with 0 Laplacian include a lot of noisy functions, in fact, infinitely many. So these boundary conditions are not really useful for this kind of smoothing application. But why focus on the Laplacian energy? We can try to find another energy whose minimizers will also solve the biharmonic equation with the Bilaplacian. The biharmonic equation is also solved by minimizers of a different energy, the new Hessian energy. Well, when I say new, it's really only new for the geometry processing on surfaces. It is old in other areas of research and for flat surfaces. The flat Hessian energy has been a staple of physics. Here is a very famous reference. The flat Hessian energy models the displacement of flat, bending thin plates. However, unlike the Laplacian energy with 0 Neumann boundary conditions, which we have encountered before, and which models bending clamped thin plates, the Hessian energy models bending thin plates that are not fixed or clamped in any way. They are completely free. More recently, we have also seen the Hessian energy being used in image processing and in high-dimensional data processing, such as machine learning. Now, this is important, so I want to restate it. This energy also solves the biharmonic equation. We are still using the same Bilaplacian. We are still solving the biharmonic equation, but we're now simply using a different energy, which will give us a different boundary condition. This is the definition of the Hessian energy. It's quite a handful, and it consists of many more terms than the Laplacian energy, including some expressions you might not be familiar with. So let's go through all of them bit by bit. It consists of the square norm of the Hessian matrix. The Hessian matrix for flat surfaces in the plane is simply the matrix of all second derivatives of a function. It's more complicated for curved surfaces, and there's a definition involving differential geometry. So if you want to know about that, I suggest you go read the reference. We also have the curvature kappa of a surface. The curvature of a surface is the product of how much the surface bends in both of its directions of largest bending, and it measures how non-flat a surface is, how hard it is to deform it into a flat surface. And then we also have the exterior derivative of a function u. If you don't know what the exterior derivative is, just imagine it's a gradient. The two concepts are dual to each other. The natural boundary conditions of this Hessian energy are the Hessian matrix times the normal vector at the boundary is equal to 0. Again, the Hessian matrix is the matrix of second derivative. So for minimizers of the Hessian energy, the second derivative across the boundary is 0. The function is linear across the boundary. For a thin bending plate, this means the plate is not constrained in any way. Contrast this with the 0 Neumann boundary condition, which says the first derivative across the boundary is 0. This means the function is constant across the boundary. And for a thin bending plate, this means the plate is clamped. Let's apply the Hessian energy with its natural boundary conditions to the same smoothing problem as before. We start with the same omega-shaped domain with the same height field, and we add the same noise to it as before. And we again vary the parameter alpha. Finally, this is the result we wanted all along. The function is denoised, but without any of the bias at the boundary. Compare the isolines on the right to the isolines in the reference solution, and they look almost the same. Well, we looked at a smoothing example on this omega domain. In the beginning of this talk, we used the Laplacian energy with 0 Neumann boundary conditions in an interpolation example. So let's see what the Hessian energy can do for us here. Here is an airplane with many holes, boundaries, and we are interpolating a function on it using the Laplacian energy with 0 Neumann boundary conditions. As you can see, this looks not bad, I guess, but near the windows of the airplane, the isolines are visibly bent. They have to be normal to the boundary to fulfill the 0 Neumann boundary conditions. In contrast, here is the same interpolation problem solved with our new Hessian energy and its natural boundary conditions. There is much less bias of the isolines at the boundary, and it's almost as if the windows of the airplane aren't there. Here is an inset zoomed on a pair of windows to highlight the situation. While the Laplacian 0 Neumann result on the left features isolines distorted near the airplane windows, this is not the case with the Hessian result on the right. The Hessian energy's natural boundary conditions, which are linear across the boundary, also result in greater stability with respect to added holes compared to the Laplacian energy with 0 Neumann boundary conditions. Here you can see two squares solving the same interpolation problem. We will now add the same holes successively to each of them. The left result, with its 0 Neumann boundary conditions, is heavily biased by each new hole added to the domain, as the isolines immediately need to deform themselves in order to accommodate the new boundary. The Hessian natural boundary conditions are better at ignoring the boundary and are thus more stable with respect to added holes. This property can be very useful when the boundaries are an artifact that is unwanted. For example, noisy holes resulting from a faulty laser scan of an object. Here is a more complex smoothing example that works similarly to the omega examples from earlier. Smoothing it with the Laplacian energy and its zero Neumann boundary conditions results in isolines that near the boundary are distorted so they can be perpendicular to the boundary. The Hessian with its natural boundary conditions, however, smooth the function as if the boundary was not there. Because of the boundary conditions, we see a sort of linear extrapolation effect across the boundary. These circles highlight the difference. On the right, the Hessian energy ignores the boundary as much as it can, and as a result, you have this sort of concentric shape that appears. The concentric structure is distorted in the example on the left by the zero Neumann boundary conditions. OK, this concludes all I want to talk about today. And let me end by summarizing the things we talked about and the things that I want you to take away from this talk. We have seen how the Bilaplacian differs from the Laplacian, and how the Bilaplacian can do some things that the Laplacian cannot. We have looked at a very wide variety of applications of the Bilaplacian in geometry processing and seen how useful it can be. We have examined a discretization of the Bilaplacian and proven its convergence under certain conditions. And we have introduced linear across the boundary conditions that limit the influence of the boundary on our result. And this is it. This is the end of my talk. I would like to especially thank the following collaborators of mine, without which none of the work on the topic that I presented during this talk would have been possible. And I would like to thank all kinds of funding agencies and companies which have funded my research so far. Thank you very much for your attention, and I'm looking forward to the Q&A.
Thank you. Thank you. That was a great presentation, Oded. It almost felt like a class at times. I was learning so much. We've gotten a lot of questions for both of you. We're going to start with a question for Astrid so that Oded can get some water or something. So you use this minimizer of the sum of the squared areas to put your virtual vertex, right? And the way you motivated this was by saying that we wouldn't want it to be outside of a non-convex shape like the centroid. And I was left wondering, is there a guarantee that the sum of the least squares areas is actually going to be inside for like a very, very non-convex shape?
So yeah, unfortunately, we do not have a formal proof for that. And inside is only suiting for planar polygons. But since we consider the sum of the squared areas, we do not have negative triangle areas we have to deal with. And the point was the solution is unique. So while not having a formal proof, it should not happen, since lying outside of the polygon would always lead to more or less triangle intersections, bigger surface areas. So minimizing those areas should always push the point back inside of the polygon.
Right.
Considering the polygon.
That makes sense. So to be clear, for your paper, are there any restrictions on the polygon shape? Like it can be literally anything. We know that it doesn't need to be convex. You said that, but like, are there any other restrictions that we have?
We have some restrictions. For example, like the definition of star shape. Like any star-shaped polygon should work, for example, non-convex. But well, if I do not have a star-shaped polygon, so I cannot like define those triangles, I will clearly have some kind of intersection. And while our stiffness metrics or our application won't crash, I will definitely have those triangle flips and bad cotangent weights. So it kind of works, but it's not. It probably the results won't be that great. So star-shaped is more or less the limitation.
That makes sense. That makes sense. Okay, so our next question is for Oded. This is a question I had. You brought up this great intuitive meaning of the Laplacian versus Bilaplacian with whether it's a rubber sheet or a thin metal plate, which of course made my developable senses tingle. So I'm wondering, is this like a physical, is there anything behind the intuition? Like how do you come to this intuition? Because you and I both know very well that a non-stretchable sheet wouldn't make that dome, right? So like, what is the physical property that differentiates this?
I must say, while I read the Courant Hilbert book that you can derive from like physical equations the reason why the bending thin plate fulfills the Laplace equation, but I don't know it by heart.
Oh, okay. So this is like a thing that's been studied.
That is an interesting question, and I think you will find the answer to it in this Courant and Hilbert book that I cited.
Okay, that makes sense. I thought it was just your intuition that you had for this, and I was very
It
surprised.
is the intuition knowing that these are the physical systems they model. I don't know the exact derivation of them by heart.
Got it. Okay, that's interesting. I definitely will look at that. So our next question is from Astrid. You do this construction of the Polygon Laplacian, which is kind of equivalent to the Laplacian for triangle meshes, and you go from triangle meshes to general polygons with this inclusion of a virtual vertex. So my question is, what about from tetrahedral to polyhedral meshes? So could I just do something very similar, adding a virtual vertex for a polyhedron?
Yes. So like this totally carries over to polyhedral. It's clearly working, and we are actually currently working on that. Like,
okay.
We have a first implementation. It works as expected, and yeah, stay tuned for
yeah.
an
That's
update.
great. That's great. No need for spoilers, but we will stay tuned to see what that looks like. So our next question from the chat is for Oded. Why just Bilaplacian? Why not keep going with Trilaplacian and Quadlaplacian, etc.?
You very well keep going. There are varieties of applications for which you want to go with the Trilaplacian. I think the most compelling one is this kind of rubber sheet property. In 3 dimensions, you will get spikes with the Bilaplacian, if I remember correctly. So in 3 dimensions, go with the Trilaplacian. I don't know if it still converges. I don't have I don't know of a proof for it, but I assume the convergence rate will also, if it converges, be worse, the same way that it decreased from Laplacian to Bilaplacian with this mixed method. But you can apply the same mixed method, just apply it twice, and you have a discretization for the Trilaplacian. Okay.
That makes sense as an answer. I just got a bunch more questions from the chat, so that's why I'm a bit confused. Okay, so our next question for Astrid is, have you considered adding more virtual vertices to the polygon, so not just one, but a bunch of vertices, so that the quality of the virtual triangulation is better?
Yes, we considered that possibility, but right now, with only one virtual vertex, we have a clear identification for the triangles. And since gradients live on these triangles, we because we can uniquely define them by the half edges of the original polygon, and the gradients live on those triangles, so we can also identify the gradients with the half edges of the original polygons. We would kind of lose this feature if we add more virtual vertices to that. So we would no longer know where are the gradients of, for example, a triangle that's constructed by only virtual vertices. So we didn't follow that road.
Okay, that makes perfect sense. So we have a question for Oded, which is, you mentioned this sigma greater than 3/2 for your proof, and many of us were left wondering what that means in like layperson's term or lay geometry terms.
That's a good question. It is, if you take the distance, our mesh approximates a surface. The goal of a triangle mesh is that basically it'll be as close as possible to our smooth surface as we can with our limited budget of triangles. Since we have a limited budget of triangles that are flat, we will not be able to represent the surface, but we judge a good triangle mesh by how close it is to the surface. This is basically this sigma. If I take the distance between each point on the exact surface and the closest point on the mesh, how large is that distance? If it is bounded by a constant times h, then your COTAN Laplacian for the Poisson equation will converge. However, if you want it for the to converge for the Bilaplacian, you need a bound that is not just a constant times h, but a constant times h to the power of 3/2. And in fact, we know that if your mesh is such that all vertices are inscribed in the smooth surface, for example, such meshes have the property that sigma is equal to 2.
Okay, that makes sense.
You can't use as many meshes as you can use for just the Laplacian, but you can still use reasonable meshes.
Okay, that makes sense. I see a question from Ante Q on the chat, who asks if the natural boundary Laplacian smoothing code is available online. I think it is, but I'll let you confirm that.
For like the airplane and stuff at the second part of it, yes, that one is online on the GitHub for the paper, and I think by now also in libGL.
Okay, that's good, and you surely can find that on your own website, probably, right?
Yes.
Okay, good. Final question for Oded is: are there situations where Neumann boundary conditions are beneficial? So I'm thinking, or the person asking is thinking, global parameterization or quad meshing, where we want the elements to align with the boundary.
Yes, there are many situations where Neumann boundary conditions are wanted. Many of them. I tried to add a disclaimer in that just because we're introducing these new boundary conditions doesn't mean that Neumann boundary conditions are bad. I want to say whenever you are working on a surface where the boundary of a surface has an actual meaning to your problem. For example, if I'm working in a pipe that has solid walls and I'm modeling like the flow of water, then the boundary of my pipe has meaning. Water can't go through there. It is an actual bound. So we want to apply a harsh boundary condition there. However, if our boundary has no meaning, for example, I made a laser scan of a surface and some information is missing and it's causing a noise, that the boundary is basically noise that we want to ignore, then the zero Neumann boundary condition introduces error. However, whenever the boundary has actual meaning, then you do want the zero Neumann boundary conditions.
That makes sense. Just so you two know, the professors in our live chat have been in full professor fashion having a long debate on the sign of the Laplacian for this whole talk. So that's just been it. So the question I'm asking are the ones not related to the sign of the Laplacian. So I'll finish with this question for both of you, which you can see coming, and it is, what about a Bilaplacian for polygonal meshes? So I'll start with Astrid. Do you, and Oded kind of hinted at this already, but do you think we can generalize your code, your method to the Bilaplacian, or even to the Hessian that Oded introduced?
I think yes. I mean, as you just said, Oded kind of handled the question already, because we also tried this version of using the Bilaplacian with our polygonal operator, and it worked. So we haven't dealt with the different boundary conditions yet, but technically it should all be applicable in any kind of way. So it already did. So yeah.
Okay, that's good. I wonder, Oded, if you can go deeper into this question, and because yes, you can just substitute the L from one to the L from another, but what about all those convergence conditions, and when you do the Hessian, you add this curvature term? What about those parts of your contributions? Do you think those would carry over to polygonal?
Yeah, I think there's two interesting questions to ask about this polygonal Laplacian in the applied to the Bilaplacian. The first one is independent of the Bilaplacian at all. Those convergence properties that we know for the cotangent Laplacian, this H square bound, does this hold for Astrid's polygonal Laplacian? That would be an interesting a question to answer. I think if this holds, then I know to me it does not sound out of the question to generalize the proof that we have here for the cotangent Laplacian, to generalize it also for Astrid's Laplacian. For the Hessian energy and its natural boundary conditions, I think, so maybe let me bounce the question back to Astrid. The flat version of this, definitely. I think Astrid's Laplacian, for a flat Hessian, Astrid's generalization immediately applies. For the curved Hessian, do you have some sort of Kruse-Rabiar element for your generalized polygons? If you do, then I think the answer is yes for the curved version of the Hessian too.
I would have to look into that. I'm not yet sure. We can probably investigate that topic, but right on the spot, I don't know yet.
If you do, then I see an easy way to generalize Astrid's polygonal Laplacian for curved Hessians too.
Okay, that's a very informative answer, and maybe you think that both of you can investigate. Okay, so that's a wrap for today. We'd like to end by thanking our artist, Byron Actionweiler, who designed this week's poster, and by encouraging all of you to join us next Wednesday at 9 a.m. Eastern Time to hear from Mirella Bengen and Rohan Soni. Thank you all very much for coming, and have a great day.